In this video, we're going to discuss energy in fluids. Energy conservation is one of the most important principles in all of physics. It arises because energy can neither be created nor destroyed, only transformed from one form into another. This allows us to develop equations to describe different systems. The basis of these being that all the different types of energy in a system, in this case in a fluid, must add up to be a constant. This is a pretty obvious principle when you think about what we said earlier. The energy can neither be created nor destroyed, so it must add up to give you a single value. Let's look at an example, kinetic energy. For a simple solid object like a ball, this is given by the familiar formula E equals a half mv squared. However, as discussed in a previous video, mass is a rather slippery concept when it comes to fluids, because the fluids are often flowing continuously. So it's easier for us to use ρ, the density, instead. Density is mass per unit volume, and replacing m by ρ leads to the equation a half ρv squared for kinetic energy. Except that now, because we divided the mass by the volume, the equation gives us energy per unit volume, or energy density, which has the units of joules per cubic meter. We can prove quite easily that this energy density has the same units as pressure, and in fact they are one and the same, energy density and pressure. The type of energy or pressure we've just discussed is called dynamic pressure because it's due to movement, that is, to kinetic energy. You can feel this pressure by putting your hand out of a moving car window. It causes a force pushing your hand back. Remember that pressure and force are closely related in that pressure is equal to force over area, or force is equal to pressure times area. We can similarly write down equations for the energy densities for all the different types of pressure which are present in a flow. And for an incompressible flow, this leads to a famous equation called the Bernoulli equation. In a compressible flow, however, as we discussed in a previous video, we also need to take heat into account. The heat required to raise a massive substance by a temperature T is E equals cmt. But again, we can replace the m by ρ, giving us the energy density. If we now write down the resulting equation and ignore some of the smaller energies which have little effect in fast flows, for example the potential energy, and divide through by ρ, we get the following equation. V squared divided by 2 plus ct is equal to a constant. This equation does assume a few things. First, it assumes that heat doesn't leak out of the system, that it stays within the fluid. This condition is called adiabatic. Secondly, it assumes that we can neglect friction or viscosity, and therefore that the entropy of the fluid doesn't change. This is called reversibility. These two conditions together lead to the term isentropic when describing such flows. And this holds true unless there are shock waves involved in the flow. So it's okay at less than the speed of sound, or where there are no obstacles in the way to generate shock waves even above the speed of sound. If shock waves are present, the second condition does not hold true. Shock waves are viscous and entropy rises because of them. However, the equation describes quite nicely why temperature rises when we slow air down in the intake of our engine, as we previously discussed. The kinetic energy has to go somewhere. It must be conserved, and where it goes is into heat. So as the velocity falls, the temperature must rise to compensate for this. This principle of conservation of energy joins three other important principles from which all important fluid equations are derived. The first of these is the equation of state of a gas. The second is the principle that mass can neither be created nor destroyed. This is called the conservation of mass and is sometimes also called the continuity condition of a continuity equation. And finally, the conservation of momentum, which takes various different forms depending on the type of flow. These principles can be expressed as algebraic equations, which are useful to solve by hand, or as differential or integral equations, which are more useful to solve by a computer. And in fact, the computer simulation of fluids using these equations in their differential or integral forms is very commonly used in modern fluid dynamics and is called computational fluid dynamics, or CFD.